All right, so in Chapter 8, Section 1, we're going to be talking about the law of sines. So back in Chapter 6, we talked about solving a triangle. So recall, to solve a triangle is to find the measure of all three angles and the measure of all three sides. So in Chapter 6, we did this where we solved right triangles. Well, we want to generalize this idea. Well, what if a triangle does not have a right angle? So if a triangle does not have a right angle, we can always do a rigid motion, which is a rotation, to lay it down with one side flat to the ground. This just makes drawing the pictures easier. It is not necessary to do this, but it does make drawing the pictures easier. So now imagine we have a triangle that looks like this, and we know that none of the angles are right angles, and we want to figure out some information. So we're going to call this angle A, angle B, angle C, and then the convention that we'll use is that the side across from angle A we will call little a, the side across from angle B we will use little b, and the side across from angle C will be little c. So capital letters are going to represent angles, and lowercase letters are going to represent lengths of sides. So we don't have a right triangle, but we could drop a perpendicular from that angle down to this side. So we drop a perpendicular from the vertex to the opposite side, and then we're going to call this H. We don't know what that is, but we can now use that to help us come up with some relationships inside this triangle. So if I look at angle A over here, we would have the sine of angle A using this perpendicular to make a small right triangle. Sine is opposite over hypotenuse. So this would be the sine of A would be H divided by B. Similarly, I could come over to angle B and calculate its sine. So the sine of B would be opposite over hypotenuse. So it would also be H over, this time, A. H can be eliminated from this system of equations. So if I solve each of these equations for H, I would have H is equal to B times the sine of A, and I get that by multiplying both sides of this equation by B. And similarly, I could solve this equation for H by multiplying each side of the equation by A. And over here, I would have H is equal to A times the sine of B. So then, if H is equal to B sine A and H is equal to A sine B, then these two things have to be the same. So that gives us the equation B sine A has to be the same as A sine B. If I divide both sides of the equation by AB, on the left side the b's reduce out, and on the right side the a's reduce out, we get sine A over A is equal to sine B over B. This gives us what is referred to as the law of sines. Oh, and I think I accidentally closed it. So on our identity sheet, if you go down into the bottom right-hand corner, you'll actually notice there is a box there that doesn't have identities in it. In fact, it has the law of sines. Well, it's got 2/3 of the law of sines is what we just wrote down, that sine A over A is equal to sine B over B. Well, it is also true that the proportion sine b over b is equal to sine c over c, and sine c over c is equal to sine a over a. All of those ratios have to be equal. So putting all of these together gives us the law of sines. So the law of sines, as we saw, works regardless of whether or not we have a right triangle or not. And it gives us a relationship between sides and angles of any triangle. So to use the law of sines, we pick two proportions. So what I mean by that is we would pick something like sine A over A equals sine B over B. We must know 3 of the 4 values in the proportion. All right, so we'll do some examples of this to help that make sense, what I'm saying, and it works better by just doing some examples. All right, so let's take a look at example number 1. So we want to solve the triangle given by A equals 131 degrees, C equals 23 degrees, and B equals 10 centimeters. Then we want to round all solutions to the nearest tenth. Okay, so it's always a good idea to draw just a sketch. It doesn't have to be accurate or proportional, and then we're just going to label all of our sides. So we have A, B, C. Then we would know that this is side A, this is side B, and this is side C. So let's fill in what we know. Our angle A is 131 degrees, our angle C is 23 degrees, and side B over here is 10 centimeters. So that's what we know about our triangle. So if we look at our note packet for chapter 8, if we go back to the very, very first page where it says law of sines and law of cosines, it's got a grid here, and it has the 5 possible oblique triangles that are labeled. So we have angle, angle, side, angle, side, angle, side, side, angle, side, angle, side, and side, side, angle. So let's go back to our example and figure out which one of these it is. So when we're determining what something is, we either need to go clockwise or counterclockwise and just read as we go. So if I start at A, I'm going to have an angle, I have a side, and then I have another angle. So this would be angle, side, angle. And notice if I start at C and go counterclockwise, I would have angle, side, angle again. So this is type angle, side, angle. So we abbreviate that usually as ASA. So if we look on our handout then, we want to find angle, side, angle. Well, angle, side, angle, that's B right here. So you don't need to add this to your notes, but I would recommend on that sheet filling these in. So angle side angle is example 1 in 8.1. And the method to solve, we're going to use the law of sines. So as we go through this, right now the only law we know is the law of sines, but we're also going to learn the law of cosines. We know which method to use based on the type. So if you ever run into a situation that is angle side angle, or ASA, we know that we're going to use the law of sines, and it's going to be similar to the example that we just did here in 8.1. Okay, so let's go ahead and use the law of sines. So as we had here, it says to use the law of sines, missing an S there, we pick two proportions and we must know 3 of the 4 values. Well, when you have angle side angle, basically we're looking at this and we need to figure out, well, which ones do we know? Well, we know side B, so in our proportion we're going to have to use B, but we don't know angle B. So we can always solve for angle B using the fact that the sum of the angles in a triangle is 180 degrees. So the first step that we're going to need to do is 1, we're going to find the missing angle. And we absolutely have to do this step first. And we know that A plus B plus C has to equal 180 degrees. So we have 131 degrees plus angle B, we don't know, plus angle C, which we do know is 23 degrees, has to equal 180 degrees. So we have 154 degrees plus B is equal to 180 degrees. So then we minus 154 and we minus 154. So we get B is equal to 26 degrees. So now after doing our first step, we know that angle B over here has to be 26 degrees. All right, our next step in resolving side angle side, or angle side angle, sorry, is to use the law of sines. To find the missing sides. So we now know all 3 angles and only side B, so we have to find side C and side A. So we're going to have to use the law of sines twice, and it doesn't matter which order we find the missing sides in. So I'm going to solve for side A, but if you wanted to solve for side C, you're going to get the same answer in the end. So it doesn't really matter. So solve for A. We're going to use our law of sines. And one thing that is worth mentioning about the law of sines, so we have sine A over A equals sine B over B equals sine C over C. We can take the reciprocal of this as well. So the proportions just have to line up. What I mean by that is either all the signs have to be in the numerator or all of the signs have to be in the denominator. So we can use this in the form A over sine A is equal to B over sine B. If we wrote it the other way, sine A over A equals sine B over B, you get exactly the same answer. This just saves us one step of algebra, so it's not necessary, it's just kind of nice. So now we plug in what we know. So we want A, so we have A over the sine of A, which is 131 degrees, is equal to B, which is 10 centimeters, over the sine, well, B, which we just solved for, is 26 degrees. So then we want to solve that equation for A, so we multiply both sides of this equation by the sine of 131 degrees. So then those reduce out, and we get A equals 10 times the sine of 131 degrees all over the sine of 26 degrees. So now we grab our graphing calculator and we start typing. And so we have 10 times the sine of 131 over sine 26. I press enter, and I get that the side A is negative 10 centimeters. So obviously something is wrong. So why am I getting a negative side length? That's not even possible. Well, it has to do with the fact, and we have to be very careful, all of these angles were given in degrees. But if I check the mode of my calculator, what mode am I in? Radians. So if we're working with degrees, make sure to change your calculator into degree mode. After doing so, if you press second enter, it'll pull up what was on the previous line. Press enter, and this time we get the correct solution, which is 17.2 centimeters. So this is incorrect. The calculator was in radians. So finally, we get that A, and we're supposed to be rounding to the nearest tenth, so that's 1 decimal place. So A is 17.2 centimeters. So now we need to solve for C, doing the same thing. So we have C over sine C, which is 23 degrees, is equal to 10 over sine 26 degrees. So once again, we multiply both sides by the sine of 23 degrees. So C is 10 times the sine of 23 degrees all over the sine of 26 degrees. And we grab our calculator. It's already in degree mode, so we have 10 times the sine of 23 over sine 26. We press enter and we get 8.91, so that's going to round to 8.9. So now we have successfully solved this triangle. So C is about 8.9 centimeters. All right, so let's jump to example number 2. We're going to start off the same way we did in the previous problem. So let's draw our triangle. And we have our A, we have our B, we have our C. And so we start labeling. So side A is 15, side B is 28, and angle A is 43.6 degrees. So in this case, we have a side angle, which we will abbreviate as SSA. So we have a side. We don't know the angle in between, so side, and angle. So if we go look at our sheet here, we have side angle, which is going to be C in our little chart. So side angle is also going to be solved by method law of sines. So this is going to be example 2 and 8.1. And it's going to be law of sines. But it's got some notes. There may be 0, 1, or 2 triangles. So the law of sines in the side angle case is called the ambiguous case because it's possible for there to be no triangles, it's possible for there to be one triangle, and it's possible for there to be two triangles. So if we look at the page just after our grid that has our method to solve in our examples, I've got some pictures that have been drawn to illustrate what can happen with the side angle. So we know a side, so the lengths of side B and C in this diagram are fixed. They can't change, and angle B is fixed and it can't change. So angle side B can change length, and this angle can change. So if we look at that picture, imagine side B rotating around angle A. It would trace out all of these. If side B is too short, side B couldn't touch side A down here. It's just too short. So in this example, we would get that there is no solution. Second possibility is, once again, sides B and C have fixed length and angle B is fixed. Angle A could change. So now imagine that rotating around, and side B might be just the perfect length to come down and touch side A exactly one time, in which case it would make a nice triangle. Because remember, side B can change length, so it would just have to shorten up to right there to make a good triangle. And then that would give us exactly one solution. The last possibility for side angle is side, we have angle B is fixed again, is now imagine angle B is long enough that when it spins around, it touches side B out here, but it goes down below side B, and then on its way back up, it would touch it again. In which case, it would make two different triangles. It would have one triangle with an obtuse angle, and it would make one triangle over here with an acute angle. So when we have this side angle case, we have those three possibilities because side B can change length, so side B could either be here or here, and then that would change angle C to match. So unfortunately, in advance, there is no way to know which case we are going to be in. That is there going to be 0 triangles? Is there going to be 1 triangle? Or is there going to be 2 triangles? The only way to know is to try to solve the problem. All right, so now back to our regularly scheduled triangle. So we're in our side-side angle case, so we have to be a little bit careful. So the first step in solving side-side angle is, notice we know two sides, but we only know one angle. So one of our angles has to be across from one of the known sides. So we have to solve for the angle across from the other known side. So our first step is solve for the unknown angle across from the unknown, or from the known side. So we set up our law of sines, and we're going to have sine B over B is equal to sine A over A. And we plug in our values. So we're going to have sine B over the length of side B, which is 28, is equal to the sine of 43.6 degrees divided by 15. So now we want to solve for sine B, so we multiply by 28 and we multiply by 28, so those reduce out, and we get sine B is equal to 28 times the sine of 43.6 degrees divided by 15. So then to undo the sine, we use the sine inverse. So B is equal to the sine inverse of 28 times the sine of 43.6 degrees all over 15. So now it's calculator time. So we have the sine inverse of 28 times the sine of 43.6 over 15. That is correct, but I put my parenthesis in the wrong place. And I get this error that says domain error. So why am I getting a domain error on my calculator? Well, let's do a little investigation and see why we're getting that and what it tells us. So when I tried to type this into my calculator, you might think, oh, well, maybe I'm in radians, but we're not. We're already in degrees. So everything there is fine. So let's get rid of the sine inverse. If I press enter, 28 times the sine of 43.6 divided by 15 gives us 1.28. Well, that's our problem. What is the domain of the sine inverse function? Well, its domain only goes from -1 to 1. So the domain of sine inverse is -1 to 1. So no such angle exists. So there is no triangle with those measurements. So then this case, we had no triangle. So this was that example when we looked on our sheet. This was A, right? We had this possibility where the sides just weren't of a good ratio of length. So side B was just too short and couldn't reach down to side A. So in this case, we had the no solution, and that can happen. So when you're doing your homeworks, that will be a choice that there is no solution. So if we ever end up with something like this where we have a domain error, it means that such an angle does not exist.